Guys, Mr. Carlson here again. Let's talk about how we can use bond energies to calculate the enthalpy of a reaction. Now, we've already talked about these right here, these energy diagrams, and how we can use these to figure out if something is endo or exothermic. So if we look at this graph right here, we see that our reactants are starting higher in potential energy than our products. And so we know that in that case, this process is going to release energy, and so it would be exothermic. It would have to release, the reactants would have to release energy overall, and so exothermic. But in this case, we see that the reactants are starting lower in energy, and the products are ending higher in potential energy, and so we would have to put energy in to the system in that case, and so endothermic. But how do we get that? Where does that come from? Well, it comes from these bond energies here. And essentially, if it takes more energy to break these bonds than it is that you're going to get energy when these bonds are formed, then it's going to be endothermic. But if the reverse is true, if you release more energy here than energy you need to break the bonds, then it's going to be exothermic. So if we look, the way to solve this, it says they give you this reaction here. They want you to figure out, is this reaction here going to be endo or exothermic based on these bond energies that they give us? Now, here's the thing about these bond energies here. So if you look at this HH bond, it says 436 kilojoules per mole. So what that means is that for a hydrogen single bond, for us to break that bond, to get rid of it, if we wanted to separate those two apart from each other, okay, if I wanted to get them separated, if they were in a bond and break that bond, well, I would need to put in 436 kilojoules of energy to break that bond. But also, the reverse would be true. If I brought these two together, okay, and they formed a bond, then they would release that amount of energy, right? Remember we talked about how it takes energy to break bonds and it frees energy to form bonds. So to break the bond here, it would take this much energy. But also, if that bond is formed, it would release 436 kilojoules of energy. So it'd be positive to break it, negative, because it's releasing it, to form that bond. And same thing for like this oxygen double bond here. This is how much energy it would take to break that bond, but also it would be how much energy is released when that bond forms. And same thing for this OH bond. Now these bond energies, they're listed in your textbook. There's tables that you can find that list out all the different bonds that we can have between different atoms, and it gives you the energy that's associated with it. Okay, so for this problem, I just have over here the ones that we would need to solve this. But for other problems, you'd be able to look up, like in your book or in a table that has bond energies, to figure those out. So right here, let's look. What we have to do is we have to figure out how much energy, we have to figure out the total amount of energy that's needed to break these bonds, energy needed to break all the bonds of these reactants, and then we have to figure out the energy that would be released when this forms, energy that's released to form these bonds. So what we have to do is we have to count up how many bonds that we have to break, right? Because for this reaction to happen, what I need to do is break apart this H2, I need to break apart this O2, and then they need to reform to make H2O. And so if more energy is released when that happens, then I need to break these, then overall exothermic. But if there's more energy needed to break these bonds than there is released, then it would be endothermic. So let's take a look first. How much energy do we need to just break these bonds? Well, I have two H2 molecules. So I have two of these, or in other words, I have two of these bonds that I need to break, right? So the first thing I need to do is I'm going to go 2 times this 436 kilojoules here, right? Because that's going to be the total amount of energy just to break these bonds for the H2. So if I do that, 2 times that 436, and so I've got 872. So that's how much energy just to break the H2, the two H2s. And then for O2, that would be a double bond, and there's only one of those. So it would just be 1 times that 498 kilojoules. So in other words, 498 kilojoules. And that's it. That's the only reactants I have. So that means I'm going to add these together here, and that's going to give me the total amount of energy to break these bonds. Let me move this down a little bit. Oh, that's right. I forgot I had this written down here. So if the energy released is greater than the energy required, then it's exothermic. If the energy required is greater than the energy released, then endothermic, which we already mentioned. But coming back up here. So adding these two together, we're going to get, whoops, hold on a second. Mr. Carlson can't do simple math. 1,370 kilojoules. Okay, now we're going to look at the other side. We have 2 H2O molecules. So for this, 2 of these molecules that we have. So in other words, I have 4. 1, 2, 3, 4 of these OH bonds, right? So I'm going to go 4 times 467 kilojoules. And for this, that's 1,868 kilojoules. So now, this is how much energy is going to be released. This is how much energy that it took to break the bonds. So there's more energy being released. So overall, right, I'm going to release energy. I'm going to release energy overall in this case. And so therefore, if I come back down here, so the energy that is being given off from the reaction that's being released is more, it's greater than the energy that we need for the reaction. So therefore, overall, it's going to release energy, so exothermic. If it was the other way around, if this number would have been higher, if it would have taken more energy to break the bonds than we actually get out from the products, then it would be endothermic. So in this case, this would be, and we could subtract these to get that 1868 kilojoules minus the 1370 kilojoules to get the overall enthalpy change. So minus 1370 would be 498 kilojoules overall. Now we make it negative technically because it's exothermic, and so that's how many kilojoules of energy would be being released from this.